Equivariant. Okay, thank you very much for the invitation. A couple of things that I wanted to say to start with. I don't remember if this is exactly the title of the talk that I gave a couple of days ago. A couple of days ago I gave a title before preparing the talk, and today I have another title after I prepared the talk, which is probably more suited. And also I should not forget to give credits to the stuff that I will discuss. So let me start with credits. So I worked with several people in these problems that I will discuss today. And one is Luis Alias from Murcia. We did together some results on bifurcation of CMC surfaces. And then Levi Lopez de Lima and Jorge Herbert. I think this is correct. There's a curiosity. I don't know if you... I always get confused when I have to write last names of Brazilian people. Usually there's they use a rich variety of last names. Every person has several last names. And so I'm never sure which one is the relevant one. But then I found out what the reason for this is. That may be curious to say. If you, I don't know if you ever asked yourself how many possible last names a language has. I found out that French and Italian are by far the two languages with the greatest variety of last names. There are about 300,000. And Spanish and Portuguese, on the other hand, are languages with a very little number of last names, probably 1/10 of that. So that explains why you have to use lots of... The Chinese is probably the language that has the fewest number. Yeah, strangely enough. Yeah. I have studied with them some other bifurcation results for CMC surfaces, and then a postdoc, Gaetano Siciliano, and my former student Renato Bettiol. I studied with them some abstract bifurcation results for equivariant problems, and finally with Levi again and Michela Zeda, I have studied a problem of bifurcation for the Yamabe problem. Okay, so all these people have contributed to the material that I will discuss today. So, rigidity and bifurcation in equivariant variation problems. The general setup that I will consider is as follows. Okay, I have an infinite dimensional manifold modeled on a Banach space. I have so this is a Banach manifold. I have a parameter space. This is a set of parameters. Could be, for instance, an open subset of a Banach space or just whatever, a topological space. Then I have a function, a smooth function, and I have G is a finite dimensional Lie group. That acts on M, say on the left. This is an action. And in such a way that F is invariant by the action of this group. So that means that F of G times X, P is equal to F of X, P for all G in the group, X in M, and P in the parameter space. Okay? And I want to find for each value of the second variable the critical points of this function with respect to the first variable. So I want to solve an equation of the following type. df dx equals 0. This is the type of equation that I'm interested in. Okay? And I will also, in most cases, assume that there is a family say given by a map with the property that okay, the pairs xp comma p satisfies this equation for all value of p. Okay. So the situation is, assume that this is P, this is M, and I have a path here, say, made of points. A point here is in the graph of this curve. If when I take this value P and I take this X, then this xp is a critical point of the function f of x comma p. Okay. Okay, and I say that, so in a sense, these are given by the problem. These are thought as like trivial solutions of this equation. This, for some reason, I already know these solutions. Okay. So I say that this family of solutions is rigid if the following situation occurs. If whenever you're given, if given Q in this parameter space P and X bar in M, such that the pair X bar P Q, satisfies the equation star, that one, and X bar Q is close to the graph or the function P goes into XP, then X bar has to be given by something of the form G times XQ for some G in G. That means if you have another critical point which is nearby, which is near this graph here, then it has to be obtained by applying some element of the group to this. Okay, there's an obvious observation is that since this function is invariant by G, then the points satisfying this equation are also G invariant. That is, if you have a critical point, then you have the entire orbit of this point consists of critical points. Okay. So what I'm saying is that basically up to taking orbits of this trivial family of critical points, there is no other critical point nearby. Okay, then I would say that this situation is rigid. And I say that there is bifurcation at some point precisely when the family is not rigid. So I say that there is bifurcation at P equals P star if there exists a sequence Xn that tends to XP star and a sequence say Pn that tends to P star, such that first the partial derivative of f with respect to x computed at the point xn comma Pn is equal to 0 for all n. And second, the point xn does not belong to the orbit of the point xpn. Right? This is exactly the opposite situation. It's this one here. Bifurcation, rigidity. Okay? So it is clear that either one of the two occurs, right? But the problem is that, and it's interesting to find theorems that guarantee that either one of the two occurs. And this is precisely what I want to discuss here. Of course, you understand very clearly that this is like an implicit function theorem, which must be equivariant. And this is a bifurcation. This is an equivariant bifurcation result. So these two things are basically settled by an equivariant implicit function theorem. And, of course, an equivariant bifurcation theorem. Now, in the literature, there's literally thousands of results of the type that I'm describing here. But there are some special properties of the problems that I want to consider that make these two problems actual, let's say. So the characteristics of the problem are the following. So the special properties that I want to discuss here. The first is that the action may not be differentiable. I will discuss explicit examples where this is a geometric variational problem. And in most of these examples, the action of the group is not differentiable. So, not differentiable action. Action in general only given by homeomorphisms and not diffeomorphisms, and possibly not differentiable but only continuous. The second is that most of the times this is not even a real action, it's like just a local action, but this is no big deal. Local action, in fact. The third property is that I'm giving up some technical assumptions on like having a Hilbert manifold, but I will not enter into the details here. So I will assume that lack of a decent Hilbert structure. I will not discuss this point today. But probably the most interesting fact here is that rather than considering a fixed group G of symmetries, it is interesting to consider a different group for each value of the parameter here. Okay? So, in fact, I have a G depending on P in such a way that this holds only for G in this variable group GP. So I have a varying group of symmetries. This is the real new thing here. Okay. What I mean by this is that I have something like a map that associates to each point of the parameter space a finite dimensional Lie group which has to vary continuously with respect to P, and I will be more precise in a second. So it has to vary continuously, and its differentiable structure also has to vary continuously. Very well. This is the abstract setup that I will consider. Now I will state abstract results of equivariant implicit function theorem and bifurcation theorem. I will basically give no assumptions, just no hypothesis, just a thesis, let's say. I will put just the relevant assumption, and I will avoid all technicalities of the object. The abstract results are as follows. So for the G equivariant implicit function theorem. Okay, the basic assumption is that, okay, you're given a solution x p star comma p star, solution of this equation. You want to assume some non-degeneracy thing, like in the implicit function theorem, but the non-degeneracy assumption has to take into consideration that the tangent space to the orbit of the action is contained in the kernel of the differential of this object here by equivariance. So you can't have isomorphisms here, okay? So the G equivariant non-degeneracy assumption is that if you take the kernel of the second derivative of f at the point x p star comma p star, this has to be equal to, this has to be as small as possible. So it has to be equal to the tangent space at the point x p star of the orbit g p star, let's say, times x p star. So a kernel as small as possible. Okay? Plus a whole bunch of other assumptions that I will not describe here. Very technical assumptions. Other nasty assumptions then. Then the conclusion is that you have local rigidity of the family around the point x p star comma p star. First result. Then I have a G equivariant bifurcation result. This is like the, say, quantitative version, which says the following. Okay, this is only proved in a very special case that the parameter space is an interval, AB. Okay? And here I have these assumptions here. First is that at the instance A and B, XA comma A and XB comma B, these critical points have to satisfy the equivariant non-degeneracy assumption. Então, equivariantly non-degenerate. Second assumption, if you take the stabilizers H lambda, that's equal to the set of elements of the group G lambda, this depends on the parameter lambda, such that G times X lambda equals X lambda, this is the stabilizer. This has to change smoothly with respect to lambda. varies smoothly in lambda. Third assumption, that if you take the Morse index of the critical point XA and the Morse index of the critical point XB, these two numbers are different. So you have, in the interval AB, you have jump of the Morse index. Okay? Then under these assumptions, there must be an instant here between A and B where you have bifurcation. And then the conclusion is that there exists lambda star in AB instant of bifurcation. And that is the first bifurcation result. But there's a better result than this, something more subtle, which is what I call the qualitative version of this. So second equivariant bifurcation result. Here you don't require this last assumption. 3 is replaced with something better. Which is the following assumption. Okay, the stabilizer, let's say, the stabilizer HA, this acts on the tangent space at XA of the manifold M, because this consists, say, of diffeomorphisms that fix XA, so you have a linear action. So you have a representation of this group on this space here, okay? And it is also clear by invariance that all the eigenspaces of the second derivative of your functional are invariant by this action. So you can construct a representation that I call pi minus of A that goes from HA to the general linear group of the direct sum of all the negative eigenspaces of the second derivative. Direct sum for lambda less than 0 of kernel of second derivative on this. So this is like I call this the negative isotropic representation, and you have the same thing at this instant P. And the assumption 3 is replaced by the assumption that these two representations are not equivalent as representations of the group. In particular, so if the Morse index is, of course, the dimension of this space. If these two spaces have different dimensions, then clearly these two cannot be equivalent. But this is a rather more general assumption here. So the thesis is that, well, if pi minus A is not equivalent as a linear representation to pi minus B, then bifurcation at some instant. Bifurcation occurs. Okay. Very well. And now I'm ready to apply this to variational problem, to real-world variational problems. Oh no, but I have to tell you first what a smooth family of Lie group is before actually. Defining what a continuous family of Lie group is difficult, but defining what a smooth family of Lie group is, this is much easier. So let me just define smooth family of Lie groups. For those of you who know the language of groupoids, this is much easier. You take two manifolds, G and M manifolds. You say that G is a smooth family of Lie groups parameterized by points of M. If it is given a smooth submersion from G to M, this is a smooth submersion. With the following properties. Well, if you define, say, G2, this is the set of points GH in G times G, such that pi of G equals pi of H. This is clearly a smooth submanifold of the product G times G because pi is a submersion, so it's transversal to the diagonal. Then you have that the map that takes GH to the I'm sorry, no, I should probably say there's an assumption 0. I'm sorry. The assumption 0 is that for all x in M, if you define Gx to be pi inverse of x, this is a Lie group. So the fibers of this submersion are Lie groups. And then here, if you take the map that takes GH in the product, G times H, this has to be smooth. And also the same thing for the inverse. And plus you need something else. The section given by S of x equals the identity of the group Gx, this has to be smooth. So a smooth family of Lie groups is something of this sort. It's a collection of Lie groups that are gathered not as the fibers of a fibration, this is important, but just as the fibers of a submersion. It's slightly weaker than fibration. Examples. This is my favorite example, favorite non-trivial example. This should look familiar to you. Okay, now I'll describe for you a smooth family of Lie group parameterized by R. Okay, so to each C in R, I will associate a Lie group with the property that if I define G to be the union over all C's of the where C times GC, this is a smooth family of Lie groups. Well, GC is defined in this way. If C is negative, then I define this to be the isometry group, the connected component of the isometry group of the hyperbolic space. This if C is less than 0. If C equals 0, then I define this group to be SON time, this is the isometry group of the Euclidean space Rn. Semi-direct product of SON times Rn. This is for C equals 0. And for C positive, I define this to be SON plus 1. Isometry group of the hyperbolic space, isometry group of the Euclidean space, isometry group of the sphere, right? Somebody may doubt that this makes a smooth family of Lie groups, but it is. It is. And this is obtained. This can be proved easily using a criterion for a family to be a smooth family of Lie groups, which basically says the following thing. Suppose that you have a fixed Lie algebra. Yes, yes. What I do is I use an embedding of the Lie algebras of these objects. Let me give you the formula here. 6A. I should have 6B at some point. Yes, this. If you take this is equal to you define this. This is a subalgebra of G, L, n plus 1 C. You define this to be 0 here, then you put minus C U transpose, R. U transpose, here you put U, here you put D, where U is anything in Rn, and D is something antisymmetric. Then this is clearly a smooth vector bundle on R. These are all subspaces of GLN plus 1. They make a smooth vector bundle on R. And for each C, this Lie algebra is isomorphic to the Lie algebra of these groups here. And basically, this is the main ingredient to prove that this is actually a smooth family of Lie groups. Okay, so you see where I want to go with this, right? Now I imagine that I have a manifold, a fixed manifold, say diffeomorphic with Rn, and I give a family of metrics to it that vary from the hyperbolic space to flat space to the spheres, and I want that the isometry group changes smoothly with this because I want to apply my implicit function theorems to this setup here. Very well. Now we're ready to see the applications of these theorems. The easiest ones are problem of closed geodesics, for instance. Oh, by the way, this here is a special case of a whole family of examples that you can construct using symmetric spaces. These are symmetric spaces of compact type, and this is their non-compact dual. This is what's behind this theory. So examples. First easy examples, for instance, you study the problem of closed geodesics on a manifold with a metric which may not be positive, like a Lorentzian manifold or something like that. Okay? So in this case, which are the objects of, that I described? Who is the manifold M? This is the free loop space, okay, on a manifold finite dimensional M. This is the free loop space of this manifold here. That is the set of all closed curves in M. Free loop space of M. Which regularity of the curves? Well, if you want to study variational problems, you have to study H1 Sobolev regularity. Sobolev regularity here. H1. Who is the parameter space? These are the set of metrics on M. Who is the group? G is S1. It acts by rotation on curves, on the right. This is a right action. Well, it's in a million groups, so no problem. The action of G on M is not differentiable, it's only continuous. Because differentiating in the direction of the rotation means differentiating the curve itself, which can't be done because you're in H1. So the action in this case is not differentiable. And what is the function f? The function f associates to each gamma and each metric G the geodesic action functional. This. Critical points of this function, for G fixed, the critical points are G geodesics, of course. Okay? This is clearly invariant by the action of S1. And what is the equivariant non-degenerate assumption here on a closed geodesic? It is precisely that the only Jacobi field, which is periodic along the geodesic, has to be a constant multiple of the tangent field. So the equivariant non-degeneracy assumption here is this. The only periodic Jacobi field has to be the tangent field. So in this case, you have an implicit function theorem. So if you have a non-degenerate geodesic in this situation, then for all nearby metrics, you have other closed geodesics. That's what the theorem tells you in this special situation. Slightly more general than this, you can consider harmonic functions between manifolds. Between Riemannian manifolds. So you have two compact manifolds, say, M1 and M2, and you take as M to be the space of maps of class C to alpha from M1 to M2. You take P, the parameter space now is the set of metrics in M1 times the metrics in M2. The group G is the group of isometries of M1 times the isometry of M2. This is a group that depends on the metric that you choose, right? You fix a metric here, you have a group here, okay? And the function associates to each function f, metric G1 and G2, the action functional of harmonic functions, which is integral over M1 of the norm of df squared. This is a Hilbert-Schmidt norm. And this involves the use of G1 and G2 to define this. So in this case, if you fix G1 and G2, the critical points here are harmonic maps. Okay? So critical points harmonic. And what is the equivariant non-degeneracy condition in this setup? In this setup, well, you have a Jacobi equation, of course, for this functional. which is a linear second-order equation. You want that the solutions of that equation are only given by Killing fields on the first, are induced by the Killing fields on the first manifold and on the second manifold. No other Jacobi field except for Killing vector fields of the ambient space. This is the equivariant notion. But actually, my favorite example is the problem of constant mean curvature embeddings. Let's say in codimension 1. So you want to study CMC immersion of a manifold, of a compact manifold M into some other manifold M bar that has codimension 1, okay? In this case, who is the big manifold M? Here you have to fix a given CMC immersion X, and nearby immersions, as we know, you can parameterize them using sections of the normal bundle, right? And if you're in codimension 1, sections of the normal bundle are just functions on the manifold. So this is just C2 alpha of the manifold M. Each function here gives you an immersion of M into M bar by looking at the corresponding section of the normal bundle and taking exponential, okay? The group G is the isometry group of the ambient space. How does it act here? By left composition. That is not exactly left composition, right? Because you take a function, take the normal section, exponentiate, then you take a composition on the left with an isometry, and then you go back, okay? And in this passage here, you lose differentiability. So the action of this group is not smooth at all. It is only continuous, okay? And who is the parameter space? Well, you can either consider a problem of letting the metric here vary, or you can let vary the value of the mean curvature. So you have the two different problems. So this is either an interval, if you want to fix the ambient manifold and study variation of a given CMC surface by other CMC surfaces with different values of the mean curvature, or you can fix a CMC embedding into some manifold and then let the metric of the ambient space vary. These are two interesting problems anyway. So two options here. Either an interval, say H0 minus epsilon, H0 plus epsilon, if you want to study fixed ambient space and value of the mean curvature changes, or you can take P to be the matrix on M bar. What is the equivariant non-degeneracy assumption here? Here, a CMC embedding is equivariantly non-degenerate if the only Jacobi fields, solutions of the Jacobi equation for CMC embeddings, are given by Killing fields of the ambient. Okay? If you are in this situation, then you can change the metric smoothly and get other embeddings. And this is how, for instance, you construct this Wente storai in, okay, the construction of Wente is for Rn, right? But then if you use this, you can extend the definition to other ambient spaces, to spheres and hyperbolic spaces, using exactly this type of result of implicit function theorem, together with the example, the basic example of a smooth family of Lie groups. So this is an important example. Yes? G? G is a compact Lie group. I'm sorry, it's a Lie group. Yes. Right, right. In fact, you have to choose here a smooth family. You have to choose only a smooth family of Lie groups. So, for instance, you take P. I'm sorry, this is not correct. As a matter of fact, you have to take P to be this groupoid made of. You have to take a family of metrics for which the corresponding isometry group change smoothly. For instance, pass from spheres to Euclidean spaces to a hyperbolic space. Yeah, you have to take here a family of metrics for which the isometry group makes a smooth family. Right, right. Yeah, this was not correct. Yeah, the same thing holds here in this case. You have to take only, not all metrics. Oh, no. Yeah, not all metrics, but in such a way that this object is a smooth family. Right, yeah. Very good. If you change the parameter of the Bezier sphere, yes, because in that case the isometry group is fixed. That is a sort of a trivial family of smooth. It would be more interesting to change from, say, Bezier spheres to other homogeneous manifolds. Which CMC immersion? Some of them will satisfy and some other not, of course. For instance, well, one thing that I was going to mention, you have Clifford tori, for instance, right? And that depends on the radius. You have CMC immersions of the two torus into S3, which depends on the choice of one parameter. And for some values of the parameter, for most values of the parameter, these immersions would be non-degenerate, but they degenerate at some point, and in fact you have bifurcation there, and that's the. So it really depends on the situation. But the thing, okay, this is. I would like to ask you. Yeah, really, I have another 10 minutes because this is an important point. Of course, I am not the first one who must have thought to a CMC. To an implicit function theorem for CMC embeddings. There are already other theorems. Most notably, I enjoy particularly a version of the theorem that I learned from a paper by Ross and Perez, but probably it's some older idea, which I will describe very briefly here. So, it is known an implicit function theorem for CMC embeddings. In this case, when you fix with this, the metric here is fixed, and you want to change the value of the mean curvature, but only at points at immersions X whose image is the boundary of some set, of some bounded subset, and you have something of this type. You have the following lemma. Suppose that M is compact. Oh, let's see. M is a compact codimension 1 submanifold of a Riemannian manifold. This is Riemannian. Then if you compute the integral over M of the product between, suppose that K is a Killing field of the ambient. If you take the product of the mean curvature times K, you integrate in M, you get 0. M has to be, this has no boundary. Why is that? Because this is a divergence. This is a divergence of the projection of K onto M. So this is always 0. plus if M is the boundary of some open subset, then there is also another integral which is 0, which is the integral over M of G of the normal vector times K. This is also 0. Why is that? Because, well, because you use Stokes' theorem in this case directly, and the divergence of K is, of course, 0 because K is killing. So you have these sort of things. So look at how you use this information if you want to find an implicit function theorem for CMC embeddings. Look at what Antonio Rosa and Joaquin Perez did. So they do the following thing. So you take the function h from C2 alpha of M into C0 alpha of M that carries a function f into the mean curvature of the surface given by f times n and then exponentiate. So to each function you associate a surface and you take the mean curvature of that function over there. So what you want to study is the inverse image of constant maps. If you want to study mean curvature of functions, you have to study this. And the point is that if you compute dh at the point 0, this is the Jacobi operator of the center immersion. And this is not an isomorphism. This is not an isomorphism because you have in the kernel, you have killing vector fields, right, in general. So what they do is they study another function, which is a function h tilde, which goes from C to alpha m times Rd into C0 alpha of m. Here d is that dimension of the kernel of the Jacobi fields, defined in this way: h tilde of f a1 ad, this is equal to h of f plus the sum of ai times g of kin, which is mean curvature plus this linear combination. These are the products of the killing fields that generate the kernel of the Jacobi operator times the normal vector. Now this function has differential, which is surjective. And why is that? Because, you see, this was not surjective because you had kernel here, okay? And now you add these objects that are exactly the things that were missing to the image here to make it a surjective operator. The thing is that the inverse image of constant function for this map may not be mean curvature functions, right? Well, that's not the case. The thing is that if this is equal to some constant h, then all these numbers have to be 0, and f must be a constant mean curvature embedding. Why is that? You use exactly this result here, because you multiply both sides of this equation here by this quantity, and then integrate. So the integral of constant times this gives you 0 by the first part of the lemma. The integral of this times this gives you again 0 by this. And so you're left with the integral of sum of ai g of kin squared equals 0. That gives you that all the AIs are 0. So what is the point here? The point is that they use this assumption here that M has to be the boundary of something. This doesn't hold, for instance, if you want to study CMC problem of embeddings of manifolds with boundary, for instance. If you have a manifold with boundary, then this is not the boundary of anything, right? Because you can't have the boundary of something has no boundary. So the same idea wouldn't apply if you wanted to drop this assumption, which in many cases may not be interesting. For instance, Fernando today was talking about immersions of RP2 that are not the boundary of anything, minimal things. So these things really happen. So does our theorem apply to the more general situation? Well, how would you set up a variational framework for that problem? You see, CMC embeddings are critical points of the area function, but restricted to the volume, to constant volume maps, right? So the variational framework for CMC embeddings is that you have to consider something like a functional f, which is of the form area plus lambda times volume, right? Because you have, this is a Lagrange multiplier. So you're studying a free variational problem of this type. What the area is of an embedding is clear. You pull back the metric and you take the volume form of the pullback and integrate. But what is the volume? Of course, if the image of M is the volume of something, then the volume is exactly the volume of that object omega. But in general, how do you define this object here? Well, you can do something of this type. What is the volume? So the question is, what is the volume? If the ambient space is non-compact, if M bar is non-compact, then its volume form has to be exact, right? So you can find a primitive for the volume of M bar, and you can define the volume of an embedding X to be the integral over M of the pullback of the primitive of this, right? If the ambient space is non-compact. And what if it's compact? Then you can do like this. You remove a point from the ambient space, then it becomes non-compact. Of course, you have to remove a point which is not in the image of your given immersion. And then you find a local, primitive, and you integrate that, right? But that doesn't work because you remember that I needed to have that this function has to be invariant by the group that acts here, right? So I have the isometry group of the ambient space that acts. And if I do this operation, then this function here will not be invariant by the action of this, of the isometry group. For instance, if you had a primitive which is also invariant by the isometry group, then everything would work fine. But this is not the case in many situations. For instance, in Rn, there is no primitive of the volume form of Rn which is invariant by all isometries. Okay? So, in fact, you have to restrict the theorem to only to those situations where you can actually define an invariant volume function. And there are some conditions more general than the one used by Perez and Ross that guarantee you this function, which are conditions on the cohomology of the ambient space, typically. So if your map has image in an open subset whose M minus first cohomology space is trivial, then you can find an invariant volume form. I'm sure that everybody of you will think that adding the assumption of the existence of an invariant volume form is something technical that's not needed, right? That you can probably prove an implicit function theorem without using any assumption on the existence of the invariant volume function. And that's because really the volume function is only needed for the variational formulation of the problem. But to define mean curvature, you don't need any volume. You just take this trace of the second fundamental form. Well, the funny thing is that there are counterexamples to the implicit function theorem for CMC embeddings when there is no invariant volume function. And there is a very easy example. Take a flat torus. And take a geodesic, a homotopic and non-trivial geodesic. Okay, so that is a minimal inversion of mean curvature 0, right? And this is non-degenerate because there's lots of Jacobi fields, but all of them come from Killing vector fields of the ambient space, because the ambient field is full of Killing vector fields. So they generate everything. So you are in this equivariantly non-degenerate situation. Now, there is no way that you can find near this zero mean curvature embeddings other mean curvature embeddings with mean curvature different from 0. Why is that? Because there would have to be circles that are projected, say, from Rn. There have to be projection of circles, of real circles in Rn, and none of them is homotopically non-trivial when you project it down. So there are counterexamples. So this existence of an invariant volume function is really essential. But I just find out that I still have maybe another 5 minutes for another important example, if you allow me. Maybe I should ask Can I just mention another quick problem, which is, okay. Let me give you 5 minutes then to show you an another example of bifurcation that I have obtained with Levi Lima and Michela Zedda, which is bifurcation. Since everybody's talking about Yamabe problem, then I want to discuss Yamabe problem bifurcation with you. So, bifurcation for solutions of Yamabe problem. As everybody knows, if you take M to be a compact manifold, then you want to study constant scalar curvature metrics inside a given conformal class. Okay, so you take G, a Riemannian metric. You denote by this its conformal class. The metrics having constant scalar curvatures are critical points of a certain functional, which is given by the Hilbert-Einstein functional. So you have a function A defined in this, into R, defined in this way. A of some metric H, that would be equal to the integral over M of the scalar curvature of H. Let's see. Now, the critical points of A in the set of metrics having total volume 1 are the critical points of the restriction of A to the volume 1 metrics are scalar curvature metrics. Okay? So H has constant scalar curvature. If and only if, suppose that volume of H is equal to 1, if and only if H is a critical point of A in, let's say, let me call this to be the set of all metrics conformal to G having total volume 1. Okay? Now, everybody knows that this functional here admits a minimum in every conformal class. But the thing is that besides minimum, there are other critical points of this functional that one may be interested in determining. And bifurcation theory gives some techniques to study these other solutions. For instance, we have proved the following. The theorem is as follows. Suppose that you start with M0G0 and M1G1 to be compact manifolds with constant scalar curvature. Say positive for the moment. Then you can do the following. You can create other trivial constant scalar curvature metrics on the product M0 times M1 by taking something of the form G0 plus lambda times G1. This is a metric on M0 times M1, which has constant scalar curvature. Okay? And you let lambda vary between 0 and plus infinity. So you have a one-parameter family of solutions for the variational problem given by this. And the theorem is that there is a sequence of values of lambda that tends to infinity, and the sequence of value of lambda that tends to 0, at which you have bifurcation from this path here. So basically you have other, so in this case, there exists lambda 1n tending to 0 and lambda 2n tending to plus infinity, instant of bifurcation for the Yamabe variational problem. And a proof of this theorem uses both bifurcation theorem, the quantitative and the qualitative bifurcation theorems in the following way. The second variation of the functional A is a very simple operator. It's just the Laplacian plus the value of the scalar curvature. So you only have to study the spectrum of the Laplacian and look at the eigenvalues. What happens is when you do this study, you prove that as lambda goes from 0 to plus infinity, there are some eigenvalues that are increasing and other that are decreasing. Okay? But there's infinitely many of them that cross 0, and so whenever you have a crossing of 0, you have a possible jump of the Morse index. You only don't have jump of the Morse index when you have at the same time some eigenvalue going from some positive value to some negative one, and the other way around, from negative to positive. Okay? But we proved that this possible cancellation happens only at a finite number of instances. So the rest of them, there's infinitely many values of lambda where you have some 0 eigenvalue of the problem. And if you add the assumption that one of the two manifolds is a symmetric space of rank 1, which are special Einstein manifolds, like spheres or all types of projective spaces, then in fact you can use the qualitative bifurcation result to prove that also at a possible instance where you have this cancellation of dimensions, let's say, you still have bifurcation by equivariant reason. Okay, that's all I wanted to tell you. Thank you very much for the attention. No. Yes, I haven't thought about it, but certainly this is a possible application of this. Yes, you study, right. There you fix the volume again and study, for instance, the area, right. I expect similar results as in the CMC case, for instance, yeah. Okay. Thank you. Ah, porque